Hello everyone, I'm Aryan Wazid and I'm delighted to welcome you to my presentation on advanced Exergy analysis and optimization of a CO2 to methanol process based on rigorous modeling and simulation. The 21st century's major challenge is controlling greenhouse gas emissions, especially the 30% rise in CO2 with fossil fuel consumption, leading to environmental issues. Carbon reduction is crucial globally, while carbon capture and storage is suggested challenges persist. This study focuses on the catalytic hydrogenation of CO2 to methanol, exploring the process's thermodynamic performance using advanced oxygen analysis for effective improvement measures and parametric optimization. The main contributions include material and energy flow, modeling, conventional and advanced energy analysis, and identifying effective improvement measures for the CO2 to methanol process. The project underscores the significance of effectively utilizing CO2 for carbon neutrality. This specifically focuses on producing green methanol and green hydrogen, highlighting their potential to cut carbon emission and tackle storage challenges. The advanced exergy analysis of the CO2 to methanol process reveals a 64.55% improvement potential, primarily addressing endogenous exergy destruction. Proposed strategies aim to decrease avoidable exergy destruction, potentially resulting in a 14.78% reduction in the total exergy destruction and a 4.99% increase in exergy efficiency. The CTM process is a reactive separation recycle system. Carbon dioxide from industrial fluid gas and hydrogen from water electrolysis are used as a raw material for methanol production. The CO2 and H2 mixture undergoes pressurization and heat after entering the methanol synthesis reaction, where methanol is produced along with parallel reactions. To manage the exothermic reaction, um, saturated deoxidized water is used for heat removal. The reactor output containing products and unreacted gases undergoes gas liquid flash separation. Most of the gas is recycled to the reactor, enhancing reactant conversion, while the remaining serves as stale gas. The liquid steam undergoes the separation and distillation for producing high purity methanol. Here we can see a block diagram of CO2 hydrogenation to methyl process. Here is an overall overview of the reaction method of our study. So, to qualify the real improvement potential and independences among the components and the whole CTM process, the workflow for the advanced exergy analysis of the CTM process is shown in Figure 2. Just the Figure 2 we have seen previously in one of our slides. The workflow for advanced exergy analysis of the CTM process involves several key steps. Number one, rigorous modeling and simulation. It is to build the equipment, process unit, and system models of the CTM for calculating the material and energy balance. Number two, Conventional exergy analysis. It is to establish the exergy balance of the components and whole system for determining the exergy efficiency and exergy destruction of the CTM process. Number three, um, advanced exergy analysis. It is to further identify the essential causes and the real improvement potential of exergy destruction by splitting into endogenous, exogenous, unavoidable, and avoidable parts. Number four, key parameter optimization. It is to investigate the effect of the key parameters of the avoidable exergy destruction from the endogenous and exogenous perspective to provide a theoretical basis and technical support for subsequent system improvement. And number five, development of improvement statistics. It is to make effective measures to reduce endogenous and exogenous avoidable exergy destruction in terms of the result of the above steps. Here we can see the calculation done throughout the CTM process, which includes the detailed parameters for the modeling and simulation of the process, and the and input parameter of the kinetic factors of reactions 1, 2, and 3. Then here we can see the driving force constant of reactions, so 1, 2, and 3, and the resulting input parameters of the uh, absorption terms of CTM reactions. And lastly, we can see the exergy efficiency and the exergy destruction ratio of each components of the CTM process. Here we can see the rigorous model of the entire CTM process with detailed material and exergy balance results presenting in table 1 and table 2, which we have seen in the calculation tables in the supporting informations. The process involves 900 kmol per H CO2 and 2700 kmol per H H2, producing 87.64 kmol per H of methanol with a molar fraction exceeding 99.99%. Emphasizing the significance of the methanol synthesis reaction, the simulation result of these reactors are compared with experimental data. When operational parameters match those in a previous study, the temperature's impact on CO2 conversion and methanol yield allies with experimental results, validating the established models for subsequent system analysis and optimization. Here we can see a diagram, a chart diagram of the comparison of the simulation results and the experimental data of reactor models. The Exergy flow diagram of the CTM process provides detail on input Exergy values for raw material, heat, and electricity. The low chemical exergy of a CO2 compared to other components resulting in a small input exergy for the CO2 stream. Due to a low conversion ratio, a significant amount of unreacted gas is recycled. The process involves separating crude methanol and producing a high purity methanol with a total exergy efficiency of approximately 66.62%. The exergy efficiency of all the components exceed 90% based on the fuel product concept as indicated in table 5 of our table of calculation. The advanced exergy analysis method is applied to overcome the disadvantages of the conventional ones. More of the exergy destruction of the CTM process can be identified as number one, endogenous and exogenous exergy destruction. Number two, unavoidable and avoidable exergy destruction. And number three, combination of splitting the exergy destruction. The study discusses the division of exergy destruction in a CTM system into endogenous and exogenous part. The results indicate that the majority of exergy destruction, which is 94.47%, is attributed to endogenous factors, highlighting the importance of addressing irreversibility within the system's component. Also, it suggests a focus on optimizing key components like the splitter, distillation column, and menthol synthesis reactor to improve the overall thermodynamic performance of the CTM process. Here, this result reveals the um, approximately 49.55% of the exergy destruction in the CTM process is unavoidable, representing the potential for improvement in exergy destruction reduction. The remaining 53.45% is constrained by current technical or economic limitations. The splitter, distillation column, and methanol synthesis reaction are identified as components with the highest avoidable exergy destruction, suggesting a need for focused effort to enhance their efficiency. This part of the slide highlights that the unavoidable endogenous exergy destruction in the CTM process constitutes the highest portion, which is 50.93% of the total exergy destruction, primarily attributed to the distillation column, splitter, and heat recovery cooler. These components are constrained by irreversibility in the chemical reactions or heat exchange. Temperature difference are not recommended for reducing due to current technological and economic feasibility. The avoidable endogenous exergy destruction, comprising 43.55% of total energy destruction, is mainly associated with the splitter, distillation column, and methanol synthesis reaction, suggesting that optimizing these components can significantly reduce exergy destruction in the CTM process. The impact of unavoidable and avoidable exogenous exogenous destruction is relatively small, emphasizing the need to focus enough on reducing avoidable endogenous and exogenous destruction, especially in components with high level of avoidable destruction. This study concentrates on the mitigating endogenous avoidable exergy destruction within CTM process, emphasizing the high proportion compared to endogenous exergy destruction. The primary focus on diminishing the adverse impact caused by internal components with particular attention directed towards the splitter and distillation column. These components have been identified as major contributors to uh, avoidable exergy destruction, making them pivotal targets for reducing strategies. By addressing the intrinsic inefficiencies avoided with these elements, the overall efficiency of the CTM process can be significantly enhanced. Here we can see like two here we can see like two graphical representation of the result showing the effective showing the effect of the recycle ratio of the performance of the CTM process and the effect of the number of theoretical and feed stages on the performance of the distillation column. And this bar chart resultant shows the comparison of the thermodynamic performance of the reference and optimized CTM process. So overall, our study shows utilized advanced exergy analysis to assess the improvement potential and interaction with the CTM process. Conventional exergy analysis resulted a total exergy destruction ratio of 33.38%, but lagged further deletions of exergy destruction types. Advanced exergy analysis identified that endogenous exergy destruction accounted for 94.47% of the total exergy destruction, emphasizing irreversibility with the components as primary cause. The study found a 46.55% real improvement potential for reducing exergy destruction, with 53.47% being unreducible due to technical and economic constraints. Reducing avoidable exergy destruction is specific component in specific components was recommended, resulting in a reduction of total exergy destruction from 48.5 megawatt to 66.9 megawatt, and an increase in the exergy efficiency from 66.62% to 71.53% after optimization. Furthermore, this study highlighted potential economic implications of pursuing improvement and suggested future advanced exoeconomic analysis to address these limitations. I'd like to conclude my presentation here and thank you for you all for listening to my presentation patiently.